This is our group assignment presentation for Basic Materials for Engineering, KIG 1004. In this presentation, we will explain about the microstructure and characteristics of electrical copper wire.
Copper is a widely used material in electrical wiring as early as the 19th century. As an electrical conductor, copper is only second to silver as the best pure metal. Due to the higher cost and lower tensile strength of silver, copper is often chosen as the core material for electrical wiring. Apart from that, copper is also a very ductile metal, which makes it easier to form into wires and allows for better flexibility. As a result, copper wiring is used to distribute power in residential, commercial, and industrial buildings, as well as mobile homes, recreational vehicles, boats, and substations. To understand why copper has such ideal properties for distributing electricity, it is vital to investigate the microstructure of the material.
Characteristic of electrical copper wire. Here we attach a schematic diagram of cross-section of copper wire, which consists of copper wire insulation, copper mesh, and outside insulation. A basic copper wire design consists of the internal copper wire, internal insulation, as well as the copper mesh and outside insulation. The purpose of the internal copper wire itself is to transfer electricity from the source to an appliance. Meanwhile, the insulation serves to prevent the electrical current from flowing to undesired place. In turn, this helps avoid short-circuiting or electrocution of the user. As stated before, the copper wire has a very high electrical conductivity and ductility, making it ideal for this application.
Next, we will explain about the microstructure of copper wire and its development. To begin, pure copper or high copper alloys are made from copper ores that are obtained from the mines as sulfides, which contain zinc, lead, and other sulfur. The ores are crushed and milled until they become a powder. A technique known as flotation separates the metal from the non-metal components of the powder. The next step is a concentrating stage where minerals are concentrated into slurry that is about 15% copper. The copper is then melted and purified in several stages until it is 99% pure copper. At this point, it is cast into anodes. Oxygen remains in the structure as cuprous oxide, but the majority of the structure is pure copper. The copper metal solidifies from the liquid state by the growth of crystals. The crystals grow in preferred directions and form open tree-like structures called dendrites. The dendritic structure is very typical of cast metals. A lower melting point mixture of pure copper and cuprous oxide, called a eutectic, forms in the open spaces between the dendrites. The eutectic particles are usually dark globular bodies dispersed in a copper background. The cuprous oxide particles form a network outlining the dendritic cells. Pores, seen as dark spots in the microstructure, are also present in the S-cast material. Referring to figure 2, the microstructure of the S-receive wire A from equiax grains, meaning that the crystals grow in roughly the same size in all directions. However, in the longitudinal plane of the drawn wire B, there is a microstructure of elongated grains along the axis of drawing. As the level of deformation increases, the drawn wire acquires a textured fibrous microstructure. The texture is symmetrical about the axis of the wire and is known as the fiber axis. Micro hardness measurements show an increase in the hardness of the drawn wires with the deformation level. This increase is very strong in the first stage of the deformation and then tends to stabilize. Now let's take a look at the processes that copper goes through. First of all, hot rolling, which is a process where a metal with a temperature above recrystallization temperature is passed through a rolling pair. When cast copper is hot rolled, the eutectic structure is completely destroyed. The microstructure of the hot rolled copper contains many small grains. Parallel straight lines extending across many of the grains are called annealing twins. They appear after a metal has been mechanically worked at a high temperature and deformed. The interdendritic network of cuprous oxide particles was destroyed by hot rolling. After hot rolling, cuprous oxide particles change form and are present as stringers or aligned rows of dark particles. The oxide particles are much larger and fewer in number than the S-cast microstructure. Next, annealing is the process of heating a metal then letting it cool slowly. As we can see in figure 4, the microstructure of copper wire after deformation and isothermal annealing, which is 9 minutes in A and 30 minutes in B. So the purpose of annealing is to remove internal stresses and increase its toughness. For copper wire, recrystallization occurs after the first minute hold, equaling 9 minutes to 260 degrees Celsius. The annealing process causes the mechanical properties of the wire to return to a state close to its pre-deformation state. In addition, the resistivity of the copper wire decreases after annealing, therefore improving its electrical conductivity. Finally, let us look at the relation between the microstructure of copper and its electrical properties. In a copper atom, the outermost 4s energy zone or conduction band is only half filled, so many electrons are able to carry electric current. When an electric field is applied to a copper wire, the conduction of electrons accelerates towards the electropositive end, thereby creating a current. These electrons encounter resistance to their passage by colliding with impurity atoms, vacancies, lattice ions, and imperfections. The average distance between collisions, defined as the mean free path, is inversely proportional to the resistivity of the metal. What is unique about copper is its long mean free path, which is approximately 100 atomic spacings at room temperature. This long mean free path increases rapidly as copper is chilled.